Hello, everybody. My name is Alex Townsend. I am a application specialist at RCC. I've been there since December of 2019. I'm also a sixth-year PhD student in the Department of Scientific Computing, and I've been at FSU forever. I came here as an undergraduate in 2010, and I've been here ever since. And so today, what we're going to talk about is parallel computing with MATLAB. If you have ever used MATLAB or you've ever done any sort of computer programming with MATLAB, you might notice that in certain applications, things like for loops and when you start having programs that have a lot of data to crunch on, it can slow down quite a lot. So what we're going to talk about today is how to break up your problem into smaller chunks that can be done concurrently on multiple cores on your computer. So the outline of what we're going to talk about today is I'm going to go over a little brief outline of what MATLAB is, just for anybody who's new to MATLAB, or for anybody who just wants a little refresher on it, hasn't used it in a while. I'm going to talk a little bit about the definition of parallel computing, the various paradigms in it, and the various paradigms of parallel computing, and how those work. And I see your question. Yes, if you actually have an RCC account and you are logged into MATLAB on the terminal, then yes, that'll work just fine for today's workshop. If you have MATLAB on your computer, you can follow along. If you have access to RCC, you can also follow along there as well. So we'll talk a little bit about what parallel computing is. I'll go very briefly through a discussion of some applications of parallel computing and places that it gets used a lot. But then we'll start looking at MATLAB specifically. We'll look at the various parallel computing options that are available in MATLAB, and we'll talk about the pros and cons of those and kind of how they work. And then I'll start going into examples. We'll look at a really simple example of multi-core programming in MATLAB, and then we'll look at GPU programming in MATLAB, and lastly, we'll wrap it up with a little discussion of what resources are available at RCC for doing parallel computing with MATLAB. So, are there any questions just to get started? If not, I will go ahead. So, as a quick reminder, MATLAB is a closed source program. It's created and maintained by a company called MathWorks. It's been around for a very, very long time now. It's also become pretty much an industry standard application for things like engineering, a lot of science applications, a lot of technical applications use it. It's very, very widely used, and it's also very widely used in academia. It's widely used in research, particularly again in the engineering departments. It'll see use in math departments as well. And normally, it's a very expensive program. I think the average license fee last time I checked is something like $700 a copy. It's kind of crazy. But luckily, FSU maintains a number of academic licenses for students, faculty, and staff who need to access it. So you can either get it through FSU ITS. They've got a process where you can get a student license through them. And also, if you want to use it on the supercomputer, RCC maintains a number of cluster-wide licenses that are available for several different versions of MATLAB. I think currently we have 2020A, 2018B, 2017, and I think 2015 and 2013. So the reason we maintain a number of licenses for a number of different versions is because sometimes code is written years and years ago, but the feature set will change in MATLAB, and sometimes the code will need to be rewritten to accommodate the newer features. Okay, so like I said, MATLAB is ubiquitous in research and industry, and it's particularly big in anything that's application focused. So you won't see it a lot in things like computer science departments. You won't see it a lot in computer engineering either, but you will see it a lot in things like chemical engineering, mechanical engineering, physics, mathematics, and various applications focused areas. And the reason for that is that it's really easy to use, and it takes a lot of the complexity and learning curve out of computer programming. If you've ever taken a class in something like C or C++ or, God forbid, Fortran, you've seen that you will see that programming can be pretty complicated, and it can have quite a learning curve if you're just coming to it for the first time. MATLAB, on the other hand, tends to make things pretty easy and pretty straightforward. And that's one of the big reasons it gets used a lot. It's also got a ton of toolboxes available. So it's got a lot of sort of pre-built functions to do things like solving partial differential equations, building, training, and solving neural networks, looking at or designing and analyzing control systems. I think Simulink is almost entirely used for that in most cases, and there's tons and tons and tons and tons of different toolboxes out there for pretty much every imaginable application these days. So as a result, it's sort of like if you've ever used R for statistical computing, MATLAB is sort of like the R of non-statistical computing. It's very easy to use, and it's very popular. So that's sort of the main reason why people use MATLAB, and the main idea of what it is. So how does this have anything to do with parallel computing? So parallel computing is something that's come along over the last several decades. It's become pretty much ubiquitous pretty recently, and more and more applications, simulations, data science, all that sort of stuff. All of that's getting to be so large that it can't fit on a single processor, and you can't really do. And in a lot of cases, you really just don't want to wait. You really just can't wait for the simulation to run in serial because sometimes it'll take years, months, years, days sometimes, and computer time, particularly supercomputer time, isn't necessarily cheap. So as a result, and also with individual processors, you can only make the processor so fast. There was a long time ago, there was something called Moore's Law, and Moore's Law basically had to do with the number of transistors you could put on an individual CPU die, and after a while, it got to the point where you could only make the CPU so fast. You can only put so many transistors into a single CPU before it got to the point where you just couldn't make it any better. So as a result, people started saying, okay, well, if we can only make one CPU so good, let's see if we can use 4 of them, then 6 of them at a time. And this is sort of where parallel computing came from. And as a result, there are 2 major paradigms today in parallel computing. There's multi-core computing and there's distributed computing. Multi-core computing is usually seen as being run on a single machine, a single computer, a single tower, and those single towers will have usually a single chip that is your central processor. But that central processor nowadays will usually have 4 or 6 quote unquote cores. And these are basically small, almost somewhat independent processors that can work in tandem with one another. However, the main thing here is that your 4, 6, 8, 16 CPU cores will all share a single memory space most of the time. So multi-core computing is usually done on a single processor, where each of the individual processes can share a memory space and access things from the same locations. Distributed computing, on the other hand, is where you want to scale your application up past a single computer. So for example, most supercomputers you hear about nowadays are actually work on this paradigm. They're computer clusters, where you basically take a bunch of relatively small but still very powerful computers with 24, 40 cores each, and you wire them together so that you end up with something that's like 100 or 1,000 or 10,000 individual computers that can all work together. So the thing about distributed computing is that if you need access, if your program needs access to some data that's being stored on the other side of the data center, it generally needs to ask for that information. It can't just directly access it like you could with the shared memory space of the multi-core computer. So as a result, distributed computing can often seem a little bit more complex because there's a lot of data request and transfer handling you have to do. So distributed and multi-core computing are generally the two major paradigms that we see today. However, and with multi-core computing, the major players in this field are OpenMP, threading, multi-threading. There are many different libraries, and almost every programming language nowadays supports threads in some capacity. OpenMP is sort of a way. It's a way to take threads and multi-core computing and make it easier to develop applications for it. It's a set of preprocessors, so it's a set of preprocessors that make that easy. So you don't have to actually mess with how the threads work. Python multiprocessing is another one that's come along recently, and MATLAB's parallel computing toolbox is primarily multi-core computing. For distributed computing, the major players there are MPI in its various flavors, either OpenMPI, MVA-Pitch2, and there's a bunch of others. There's also MATLAB's parallel server. So parallel server is sort of MATLAB's version of the distributed parallel computing toolbox. So, especially in recent years, you might have heard a lot about GPU computing. So GPU computing is often, if you ever take a parallel programming class, generally it'll either not be covered at all, or it will be covered sort of as its own section right near the end. And that's generally because it's sort of treated as its own paradigm, even though if you wanted to be really pedantic and technical about it, it is technically a kind of multi-core computing, because GPU cards are they're essentially graphics cards, but they're sort of really souped up graphics cards. And essentially they're things that have they're little cards that have a whole bunch of little compute cores that are very, 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 very good at matrix computations. And so if you send a big matrix calculation off to a GPU, it can be broken up across hundreds of these little tiny GPU cores. And that can generally speed up your matrix calculations quite a lot, and can even outperform multi-core and sometimes even distributed computing, depending on how many computers you distribute your work across. The other minor paradigm that you hear about these days is hybrid computing. And so basically if you think multi-core is good, so for example, if you have a supercomputer and you've got a whole bunch of machines, but each of those machines also has 40 individual cores you can use, why not use all the computers and all the cores? So hybrid computing makes it possible to mix multi-core and distributed computing. So what you'll do is you'll take your problem, break it up into little bite-sized chunks, send those off to each of the computers, and then the computers themselves will break up the problem even farther and send those off to their individual processor cores. This can be quite complicated to handle correctly, and the programmer time complexity gets can be very, very bad, particularly if you're really new to it. So common approaches for this are hybridizations of MPI and OpenMP. MPI and threads, MPI and GPU is another big one, where often MPI and GPU is used for programs that need to make use of multiple GPUs at the same time. MPI, this kind of hybrid computing generally shows up in applications that absolutely positively have to be as fast as possible. And generally those are applications where the data size is absolutely enormous. And sometimes even the data size can barely fit into memory, even on 10 computers. So in this talk, we're going to focus almost exclusively on multi-core programming, and there's a reason for that. I'll get into in a little bit. We'll also talk a little bit about GPU computing, but mainly multi-core. The main reason for talking about these two is because the same parallel computing toolbox can be used for both. So the main reason we're going to talk about these two and not distributed computing is mainly because RCC only has a license for the parallel computing toolbox, not the parallel computing server. So I can't exactly go into examples with parallel server. So I'd like to be able to do things I can give examples on. So before we go into applications, are there any questions? If not, I will continue. So what are the major applications of parallel computing? So parallel computing gets used all the time in almost every place computers are used. So good examples of this are in engineering, you might have to solve the Navier-Stokes equations for complex compressible flows and wind tunnel simulations. The main reason for that is like if you've got an airplane model and you're trying to figure out whether or not it'll fly at supersonic speeds, you'll need to solve the Navier-Stokes equation for compressible flows, and depending on the size of your solution domain and depending on how long you want to run the simulation for, and depending on the complexity of your model geometry, that can get really computationally intensive. So in cases like that, if you're trying to run this on a single machine with one core, it might take forever. It might take decades. So in cases like that, you might really need parallel computing, and you might need really large-scale parallel computing. In business, for example, Monte Carlo simulations are often used for portfolio optimization, and they're also used a lot for macroeconomic modeling. In science, parallel computing gets used a lot in chemistry and bioinformatics. You'll see molecular dynamics and quantum chemistry simulations for materials and chemical characterization. Parallel computing gets used in those all the time, because particularly when you're trying to solve things like when you're trying to solve Newton's equations in molecular dynamics for 1 million particles, for 1 million individual atoms, that can be really time consuming. And with quantum chemistry, if you're trying to solve one of the various approximations to the Schrodinger equation, you really want to, that can also be very time consuming, particularly approximations to the multibody Schrodinger equation. Another place this gets used a lot in science is image processing. Image processing is actually both a good example for parallel computing and a good example for GPU computing. Image processing gets used. Some of the biggest applications for image processing I've seen have been in cryogenic electron microscopy. And if anybody's here from the Institute of Molecular Biophysics, you might have seen this before. Some of their programs to characterize 3 structures of proteins and enzymes they actually use a really interesting combination of both parallel computing both hybrid computing and GPU computing, because their data sets are absolutely enormous, and they need those programs to be as fast as possible. In the social sciences, deep learning for large and complex psychology, linguistics, and education data sets is a common application for parallel computing. And even in the arts, RCC actually once had we had an undergraduate student do a research project on using deep learning and natural language processing to determine which of the purported works of Shakespeare were actually by Shakespeare and which ones were by one of Shakespeare's proteges or students. So even in the arts, parallel computing and large-scale data science is very common and very important. So in MATLAB, there are a number of different parallel computing options available. So the parallel computing toolbox is the one that we're going to be talking about today. It's sort of the main parallel computing method that you'll see a lot of in MATLAB. It supports multi-core programming. It supports GPU computing, and it supports and it also can be used, and it can be used in tandem with the parallel server with a parallel server program to support what am I trying to say? Sorry. To support distributed computing. We will not look at that today. We will be looking mainly at the parallel computing toolbox. And that, as I said, is mainly because we are at RCC, we don't have support for the we don't actually have support or a license for the distributed parallel server. So we'll have to just stick with what we got. So multi-core programming in MATLAB. So let's look at a simple serial code. This is just a simple example of a program that it's basically adapted from the parallel computing toolbox's documentation. It's just a simple calculation that kind of approximates a time-dependent matrix calculation. So if you want to calculate 10 time steps and you need to do this calculation where you're sort of updating this value at this matrix A. So this calculation has a with 500 elements and it updates this with the maximum of the absolute value of the eigenvalues of a random matrix that is 100 by 100. So this will take 26 seconds to run, and so it's not really that bad. But if you start playing with these numbers, particularly capital A and little n here, if you start playing with those and adding too many more numbers, this number gets really big really fast. And so if you make this 5,000 or 1,000, you will start getting to the point where this will start taking many, many minutes. And if you put too many zeros, it will take hours. So this kind of code I chose this because it's really simple. It's based on the documentation and guaranteed to work. And also because this sort of construct where you have a while loop and within a for loop, this kind of a construct is actually very common in solving time-dependent partial differential equation problems. So examples of that are like if you're trying to solve the Navier-Stokes equations, like I said before, this is the kind of construct you might see. If you are trying to solve the time-dependent heat equation, you might see this here. So this is just a really simple example. And like I said, it runs in 27 seconds. But can we do better? 27 seconds is great, but can we get that down to something can we make that run a lot faster? And yes, we can. If we use the parallel computing toolbox to parallelize that inner for loop over as many cores as our computer has, and the HPC node I was on when I ran this had 12 at the time. So what would that look like? in order to go about that, we can use something in MATLAB called the Par4 loop. And Par4 literally is just a portmanteau of the words parallel and for. So one of the reasons MATLAB's parallel computing methods are so nice is that it basically it makes turning a serial program into a parallel program really simple, because all we really have to do is take this for loop and turn it into Par4. Now, there are a couple of very important things to keep in mind here before we do that. In some cases, you can just take for I equals 1 to n and replace it with Par4 I equals 1 to n. However, you need to be very careful if you do that. If we go back to this serial code example, you can see how if you're not really careful about how you're updating this A matrix, you might end up with a situation where the update actually where the order you update A in depends on where the order you update A in is dependent on the loop iteration. So, for example, if you break the for loop up into a bunch of different processes and they run at different speeds, you might end up with situations where you get the wrong answer. And I'll show you a little bit about why that is. So, for example, if you have process I and process J, and you've got this big array here, and you have process J working on J to M, and you've got process I working on 1 to I, then if you're doing something like normal partial differential equation calculations, for example, normal finite difference methods, you will end up in a situation where once you get to I, you'll end up needing the value of the array immediately after I and immediately before I. However, if process J got there first and updated the value of I before you did, all of a sudden you're in a situation where this value J is the wrong value. So you need to be really careful to make sure that. So you would need to be really careful to make sure that this loop can be done in any order. And the way that I've done this to make sure that this kind of a situation doesn't happen is by updating a copy of the original array. That's just a really simple way of doing parallel computing, and that's a very simple way of kind of removing iteration order dependencies in for loops. So as long as we're sure that update speed errors, and this sort of thing actually has a term. This is called race conditions. What that basically means is that when you have situations where one process needs the old value of something that another process is updating, it's sort of a race to see which process gets there first. And sometimes you'll get the right answer, sometimes you won't. It all depends on which process gets to that piece of data first. So since we're sure that we're not going to have race conditions in our loop because we're updating a copy, not the original matrix, in this case, we actually can just replace for in that for loop here with Par4. So if we do that with the same setup, 500 n equals 500, a equals 100, and we're going through 10 time steps. If we run this now, we see that the speed is now, it runs in about 4 seconds as opposed to 27. So this is a little bit more than 7 times faster. And this is with 12 cores. So if you had, 24, 48, 64 cores, this number could get really small. And this is really advantageous because when you start messing with these numbers n and a, and you start making them really big, you will you'll see that parallel computing, you'll see that running this in parallel actually does really help deal with keeping the runtime down to a reasonable level. So, like I said, as you can see here, so for complex calculations with large data and parallel computing with multiple cores, for complex calculations, this is sort of a toy example of something that could very easily become very complicated very quickly. But for calculations that can get very complicated very quickly, parallel computing with multiple cores can really speed up our calculations. And this sort of thing shows up in programs all over the place, not just MATLAB. Like I said, almost every programming language nowadays has some facility for parallel computing. So before I go on, are there any questions so far? I'm sorry I couldn't pronounce the word support there a few minutes ago. My brain just decided to explode for some reason. If there are no questions, then I will continue. So before I go on to distributed computing and GPU computing, let's actually run an example of this on the HPC. So real quickly, can everybody see my terminal here, or is it still showing the slides? Or is it showing both? Okay, hang on a second. Is that better? Really? Okay, cool. Perfect, thank you. Okay, so if we look at this particular code that I've been talking about, I have it in run simulation.m. If we look at this code here, we can see that we have this function called testmat. This is basically just a function I wrote to test MATLAB to see how fast and this will give us a timing for how fast the program will run in serial, in parallel, and eventually on the GPU. Now, I will comment out the GPU part because for one of the things, because we'll get to why in a minute, but we're going to look mainly at the parallel version of this code and the serial version of this code. So if I pull up MATLAB on the login node, I'll probably have to share this again, but it should pull up this, and it should be fine. The default, by the way, if any of you are on RCC right now, the default MATLAB version right now is R2020A. This is the most recent version we have available. And I think it is the most recent version. Okay. Come on. Okay, so here's that function I was talking about before. And By comment out, I mean delete. I'm going to delete that and that. Okay. So let's go ahead and, so I'm going to go ahead and run this really quickly. You can either just type this into a normal script, or you can type it out, into a function. Matter of fact, I'm going to do that. I'm going to type this out into just a regular script. Oh, I forgot. This is the one thing that can be kind of annoying about MATLAB if you're coming to it first time, is that the controls for cut, copy, and paste are very different from what you would expect. They're not control C, Control X, and Control F, which has always gotten to me. So let's take this serial code, for example, and let's run it, and let's make sure that the timing that I promised you is correct actually is. Boom. Interesting. So in serial, this has decided it wants to run in 4 seconds. Why is that? That's interesting. What did I do wrong here? Well, originally this worked. Sorry about that. Anyway.
Hey, Alex, we have
yes.
A couple of comments and questions in the chat.
Okay. Yes, let me look at that. Okay, so which MATLAB commands can't be used inside the Par4 loop? So there's a couple of things with MATLAB that you can't do inside a Par4 loop. One of the most important things with that is you cannot nest Par4 loops, at least not easily. So, for example, if you try and write it, so for example, if we go back to this if you had a second for loop in here, like for j equals 1 to n, then writing par4 I equals 1 to n and then par4 j equals 1 to n too. That is not something you can do directly. You can kind of nest Par4 loops, but you have to kind of do that. It's kind of messy as to how you have to do that. There are a few commands that can't be used within Par4 loops, but I do not remember off the top of my head exactly which ones those are. I think those are mostly things from other toolboxes. Any other questions? Okay, so if I were to, so let's see if I can get back into this MATLAB thing here. So if I go to this test mat function and I run simulation, I have it set up to say run simulation S. And why does it not like that? What happened here? Go figure, everything works fine until you need to use it. Oh, yeah, sorry, let me do that real fast. There we go. So here's MATLAB. You can actually, if you look at the so if you look at this test mat function, you can actually look at the various functions and variables, and so we can actually play with these numbers a little bit. Let's make that n 5,000 instead of 5. Let's see what happens. As you can see, taking its time. Oh, hang on. So if I were to run this, it's actually very fast. With 5,000, it's decided to be very, very quick within about 4 seconds. If I make that A much, much larger, let's make A and N really big, and let's see what happens. This is just the serial code. That's about 46 seconds. Let's make it even bigger. Let's try and get to the point where either MATLAB breaks or this takes forever. Here we go. That's better. About 4 seconds. So now if I were to try and do this, let's just make N even bigger. A couple more orders of magnitude. This should take about maybe 40 seconds or so. And then once we have this, we'll go ahead and put this into the parallel example, and we'll see how the speed up works. MATLAB can at times be very picky and very, very, very temperamental. So it's worked before, so we'll see if it works now. And while we're waiting, are there any? And while we're waiting, please feel free to ask any other questions. Make this a little too big. Bring that down 1 order of magnitude. So actually, that's the. Oh, you are right. That should be RAND. That makes so much sense now. Thank you so much for catching that. And here I was starting to think I had really angered the gods, the computer gods. Thank you so much for catching that. So here we go. If we keep this at 500, if we keep this at n equals 500 and a equals 100, then we'll end up having to sit here for a little while. And in about 20 seconds, this should kick out a statement that says ran in 26.83 seconds. So this little calculation we have here is pretty simple. You're basically taking a random matrix of size 100 by 100. You're taking the eigenvalues of that, which is basically taking it, which will give you a 1 by 100 array, and then you're taking the absolute value of those eigenvalues, and you're taking the maximum of them, and from there you're updating this A new matrix with the previous value of a array A. So this kind of calculation is it's just a little toy example for how you can get kind of complicated calculations into MATLAB and how you can have these sort of time dependent calculations that have to be done over and over and over again. And but the absolute value of eigenvalues, this sort of thing shows up a lot in quantum mechanics. So if you're going to end up doing any quantum chemistry, you'll end up seeing a lot of this sort of stuff. So let's so this ran in 26 seconds, and that's fine. But let's see what happens if we run this in parallel instead. If we run this in parallel, then it should run quite a lot faster. Now this thing over here, the parallel pool, this is actually something that's fundamental to MATLAB when it comes to parallel computing. Whenever you start doing parallel computing, whether it be multi-core or distributed computing, MATLAB will have something called a profile. that profile basically is it's a little file that MATLAB will read that tells the program which where the processors and where the memory is that it's going to be accessing. So the reason MATLAB does things this way is actually because this is part of how the parallel computing toolbox can actually work with the parallel server to run distributed computations without having the user have to know anything about MPI or message passing or networking or anything like that. So one other important thing that you may have noticed is to keep in mind is that if you're running a parallel calculation and you're just starting the parallel pool here, you might run up against something like this. Now, you see here it says elapsed time is 46.469 seconds. Well, wait a minute. The serial one took 27 seconds. What happened? Now, this is actually a kind of a weird thing that can happen with MATLAB sometimes, is that when you first start up a parallel pool, which is done implicitly with this Par4 function, it will take some time to spin up the processors and to spin up the memory and to get everything straightened away. And if you're running a timing function, which I am here, tick and talk is how you do timing in MATLAB. If you notice, I start the timing long before I start the Par4 loop, and I end it after this whole while loop is started. So this whole timing function hasn't told me anything about how fast this Par4 loop takes. It's told me how fast the Par4 loop takes plus the overhead for starting the parallel computing pool. So as a result, you can end up with really weird numbers that look like this, and well, if you're seeing it for the first time, it can be really scary, and you'll think, oh my God, what did I do? However, the best thing to do is just once that parallel pool has started in your MATLAB session, it will stay there until you either delete it or you disable or you close MATLAB. So if you see weird numbers like this, the best thing to do is just run your program again and with the timing, and it should give you a much more accurate number. Like we see here, it went from 46 seconds down to 3.9 seconds. So now that the parallel pool has started, we know for sure that this whole tick and talk thing here, this is actually measuring how long this function takes in parallel, as opposed to parallel plus all the overhead for setting things up. So this is just one example of how parallel computing can really, really speed up your calculations. And so, will this happen every single time I start running a new program, or will this only happen for the first program I run using Par4? It depends. If you start MATLAB, like the graphical interface here, and you run a single program with Par4 in it, then the first time you run any program, you'll end up with that timing weirdness. However, for every subsequent time within the same MATLAB session, you'll end up being fine, and the timings will look right. But it won't happen. So it won't happen every time you start running a new program. It'll only happen every time you start running it. It'll only happen every time you start a new parallel pool, which is usually only once a session. So for example, if I were to close MATLAB and reopen it, then I would end up with that weirdness. I'd end up with that timing weirdness again. But since I'm still in this session, if I could run this parallel code as many times as I want, and it should give me exactly the same answer or very, very close to it. Yep, 3.75. So another question, do you suggest that I run a small and simple Par4 program to establish a pool? Actually, MATLAB has a function to let you do that. So one thing I could have done here is I could have actually started a parallel pool way before this by doing par pool 12 in this case. And then what this will do is it will explicitly start a parallel pool for use later on in Par4. Actually, best practice is probably to do this, to make sure you start your parallel pool right at the beginning of your program, or right at the beginning of your script before you do any heavy computations and before you do any timing. Sure. And then also, if you explicitly start a parallel pool like this, if you're going to run a program non-interactively, if you just want to type it in the command window and just let it run, it's usually good practice to also do delete GCP. And what this delete GCP function does is it'll delete the parallel pool for you. And this is just a good way. This is just best practices to make sure that that parallel pool only exists within the parts of the code that you want it to. So, any other questions? If not, I will go back to the slides. This is showing the slides, right? Okay. So far we've looked at just a basic serial compute. We've looked at a basic serial code that runs in a reasonable amount of time, but it can be pretty slow. But it can be pretty slow once these n and a numbers start getting really big. If I started putting n equals 500,000 or a equals 500,000 here, well, first MATLAB might actually break. That's one thing that does happen every now and then with MATLAB. MATLAB uses Java quite a lot for a lot of its processing, and so as a result, if you use a matrix size that's too big, it can sometimes crash MATLAB. So if I were to make, probably not n, but if I were to make a something like 100,000 or 10 million, then it would either take forever or just straight up crash MATLAB. So we also looked at the parallel version of this code, which really speeds up the computations, makes things run a lot faster, and it's really easy to do too. With all we had to do for this was just make sure that the order in which the iterations are done really doesn't matter, and we did that by making a copy of this a variable that we were using, so that we weren't updating anything in place. And then all we had to do was change for I equals 2 to n to par4 I equals 2 to n. And MATLAB, with its parallel pool and everything, took care of everything in the background and gave us a factor of 7 speed up. So a quick word on distributed computing in MATLAB. So many of the same constructs we just looked at, Par4, there's a bunch of other ones, there's SPMD, there's a bunch of others. I'm really only focusing on Par4 because it's one of the more common ones you're going to see. And it's by far, and parallelizing for loops is by far one of the most fundamental things you have to do with parallel computing. If anybody has ever programmed, if any of you have ever programmed an OpenMP, you'll know that it is largely about parallelizing your loops. So many of the same constructs that exist in the parallel computing toolbox will also work for distributed computing. And as I said before, this is really because of that parallel pool that often does really weird things with your timing. It will, because of that, because of the way that MATLAB works, it can set up a core, it can set up a cluster that kind of looks multi-core to MATLAB's parallel computing toolbox, even if those cores are on a bunch of different computers. So as a result, you can use Par4, you can use SPMD, you can use you can use GPU array, all of those things you can use on the distributed computing, toolbox as well. And this kind of thing can be really useful for scaling those kinds of calculations up to really big domains. If you really needed A to be 10 million, or if you really needed N to be a quadrillion, you might really want to think about distributed computing. And for example, if you were solving the heat equation is just a simple mathematical model of how heat conduction through a material. So if you have a simple domain that's just you seeing how quickly heat will transfer across the wall in your apartment or something, then that can be done pretty quickly. But if you want to see how quickly heat from the core of the planet is going to make it up to the surface, that's many kilometers and might take decades of simulation time. And so for that, you might want to think about distributed computing. And as I said before, because we don't currently have a license for the parallel server, so we'll not talk about that today. Now, a word on GPU programming. So MATLAB's parallel computing toolbox is really nice because it also comes with support for GPU computing. If you've ever done GPU computing in other languages, normally C, C++, and Fortran, you've probably seen that the way you do GPU programming is really different from how you do normal parallel computing with things like OpenMP and MPI. And this is really a facet of how the languages for GPU computing have developed. The two major ones there are CUDA and OpenCL. Those are the two big famous ones. However, MATLAB has actually taken that really different way of doing things and wrapped it really nicely into the parallel computing toolbox. And in doing that, it's created this construct called GPU array, which is really nice. If you take that array A, for example, from this example here, if you were to take this A new or this A and you were to turn it into a GPU array, then all of a sudden that array now exists on the GPU. And then you can just call all the normal functions you would normally run in parallel or in serial on that array, and those calculations will then be run on the GPU. So we can try and do that. I can't promise that this example will not be any faster on the GPU than it will be on the CPU, and the main reason for that is that this is not a big enough calculation. GPU computing really becomes useful when you have quadrillions of calculation, or you have millions or billions of calculations to do, quadrillions maybe, and it's really useful for certain types of matrix calculations. Random matrix calculations like this, probably not so much, but we can try it anyway. Let me bring up MATLAB, and let's quickly turn this into a GPU calculation. I might actually have to move this. Let's see. So if I were to take A equals 0 is 1 to n, and instead I wanted to make this a GPU array, all I would have to do is say A equals GPU array A, and I could say A new equals GPU array zeros 1 to n. So now, if I were to run this on the GPU, which I'll do in a minute, this would all the calculations that I do, any calculations I do on A and A new should be done on the GPU. Just to be really safe, we're going to also put this A matrix on the GPU as well. So we're going to say within the for loop, A equals GPU array round A. So now, quickly, I'm going to turn MATLAB off because I have to get onto a GPU node for this to work. Okay. So one thing to keep in mind if you're doing this on RCC is that all of our login nodes, which will be HPC login 24, H22 login 25, and HPC login 26, none of those have GPUs on them. The GPUs are only on the compute nodes. So if I were to run something like this command, this srun command. This command is just a quick command for me to get an interactive session on one of our GPU nodes. So if I do that, it should give me a GPU node. Quickly there. So now you'll see that this HPC login 24 is changed to HPC i3615. I3615 is one of our general access GPU nodes. Actually, no, I take that back. It's one of our backfill GPU nodes. So if I do MATLAB no splash, no desktop, then this should open MATLAB in the terminal for me. And then we can try that GPU function. So let's go ahead and let's do that. I had it as run simulation T. So this will run all of this. So this will run all of those simulations. Actually, if I go here, software, MATLAB. So because I'm doing this in the terminal, I'll make sure that we have the GPU code up on the screen as well. So the serial computation took 28 seconds. There's a parallel pool starting up, which is probably going to take a good 40 seconds, as it usually does. I'll run it again. I'll run it again when it does that. Actually, hang on a second. Let's do that. I'll actually follow the advice I give and do par pool. Delete GCC. So now let's see about running this. What is that? Run simulation T. So now it's going to start the parallel pool. And what does it not like? Oh, yeah, that's another thing I forgot about. MATLAB and compute nodes do not always work together very well. I don't remember why that property is set to one worker. But we're just gonna. This is really just a test. We're gonna run. We'll just run this to see that it really will run on the GPU. Like I said, it may not actually be faster, but it will. This should illustrate the fact that you can do these calculations with GPUs as well, and it should illustrate that by all you actually have to do to run these kinds of calculations on a GPU is just turn your arrays into GPU arrays, and then you can just call functions on them like you normally would, and it will be just as fast. And it will be, if this were a calculation that was going to be really well suited for a GPU, then it would be very fast. So we see that the serial calculation has taken about 29 seconds. The parallel one is probably going to take about that same amount of time because we only have one worker right now. Yep, about 30 seconds. And now the GPU calculation, which, what did it not like? Oh, no, sorry. Run simulation is the name of the code, is the name of the program that I wrote here. So what I would do is just type this code out that I'm highlighting right here into your script, and then run it from there. What did I do here? Oh, the size of the vector should be a row. So let's do, let's do AMAT equals GPU array mat and A and AMAT. And because I don't want to wait for that to do that again, there we go. It's just not. Oh, yeah. That's another thing with a par4 session is that if you do that once, you might need. There we go. So like I said, this little toy problem here isn't all that well suited to a GPU, but I'm doing this because it's relatively simple, and also because I just want to highlight the fact that turning a serial or even a parallel computation into a GPU computation is actually really easy to do in MATLAB. All you got to do is turn your arrays into GPU arrays, call the normal functions, and it should go eventually. So there we go. Took about 46 seconds. That's like I said, that's not because the GPU is bad or the GPU is slow or anything. That's just because this problem isn't well suited to it. So hopefully this shows that that running calculations in serial, in parallel, and on the GPU is actually really easy to do in MATLAB. And for example, if this little toy problem here was something different, was maybe trying to do 3D reconstruction of a protein from 100,000 microscope images from a cryogenic electron microscope. This would be a really easy way to run that kind of a calculation. If you needed to train a neural network with 1 million different pictures, this kind of GPU array construct is another thing that would be really useful there. And the best part about it is there's not much of a learning curve. You just have to know how to use call GPU array, make sure you're on a computer that's got a GPU, and you're off to the races. So, oops. As I said, really big matrix calculations, particularly matrix calculations that are sort of well behaved with really good condition numbers, and also matrix calculations that are graphical in nature. So things like 3D matrices and 3x3 matrices. Those are really well suited to the GPU, and those show up a lot in, like I said, image processing and deep learning. So before I go on, are there any questions so far? Does MATLAB support OpenCL or CUDA for GPU? As far as I know, right now it only supports CUDA. There may be a version of it that supports OpenCL. but it's mainly intended for NVIDIA CUDA GPUs. Maybe hopefully in the future they'll have support for either AMD GPUs with their, I forget what it is, ROCm, I think. And no, you do not need to specify. You do not necessarily need to specify CUDA in the. You don't need to specify CUDA or anything in the MATLAB code itself. If you are on the GPU, you do need to run. This might actually be why this broke. You do need to run module load CUDA, and that will load the current CUDA version on RCC. But no, in the actual MATLAB code, you don't need to specify CUDA or do anything like that. Any other questions? Yeah. I'm actually just curious right now if this runs faster. Probably not. So yeah, just as a quick aside, if you're running on RCC, you do need to make sure to load the CUDA module before you try and run any GPU calculations. What this will do, all this does is it just makes sure that our CUDA installation and all of the necessary headers and drivers are in the path that the GPU and MATLAB can find. So, as a quick wrap up, we might get done a little bit early today. There are various RCC resources available for parallel computing. As I've shown in these examples, RCC has a bunch of compute nodes that have somewhere between 12 and 48 cores available. You can use our Slurm job scheduler to get access to however many cores you need on our compute nodes. And you can also access our various GPU nodes. And each of those GPU nodes have 4 GPU cards available. And currently the GPU cards that we have are all GTX 1080 Ti's. Another really interesting resource that we've only just started to roll out is a system called Open On Demand. And Open On Demand is really nice. Because instead of having to mess with this terminal and having to worry about Unix commands and whether or not the MATLAB window will open or not, you can actually just go to ood.rcc.fsu.edu, and it will pull up a window that looks like this. So you'll see Open On Demand, jobs, clusters, interactive applications. And if I wanted to, I could just click on interactive applications and click on MATLAB. And this will eventually take me to a little session here. And what this will do, it'll take me to a little page here. And what this will do is it will say, okay, you want to run MATLAB. Tell me what partition you want to run it on. Tell me how long you want to run it for. Tell me how many cores you need. And tell me what version of MATLAB you want to use. So let's say I want to use MATLAB 2020A. I want to use the general access partition. And I want to run it for 1 hour. And I want 4 cores. Then I can hit launch. And what this will do is it will say, okay, I've created this job for you, and what the job will then do is it will sit in line until the necessary resources are freed up for you. And once those resources are freed up, this session will start, and it will jump you immediately to a MATLAB window, almost exactly like you'd run on your desktop. This might actually take a while, so I'm going to go back to MATLAB, and I'm going to try and run this on. One of the things with supercomputers is that supercomputers are all shared resources. So that means that if the resources are being if the computers are being really heavily used that day, sometimes you'll have to wait in line for your job to start, and sometimes you kind of have to play musical chairs with the partitions to find one that'll start really quickly. So backfill 2 has been really good to me so far. So we'll see if this starts. So where do you get the partitions from? So that's a really good question. There is a partition list. If you go to rcc.fsu.edu and you go to support/documentation and you go to documentation, and I'll link this in the chat as well. And then you go to HPC partition list here. This will give you a list of all the available HPC partitions and whether it's general access or an owner-based partition. Well, it would if the website decided. Well, what if the website wanted to work today? There we go. So, owner-only partitions are those that you have to have. You have to have the owner's permission to access. But anything that's general access, you can generally use at your leisure. Let me post this link in here. And I'll go back to Open On Demand. And so now what I can do, now you see the job is running, and I can now hit Launch MATLAB, and it'll bring me into this VNC session, which is just a web browser that lets you look at your program. And now you can see that I'm now running MATLAB in a interesting window. That's not quite sized right, but okay. And you can see that I'm now running MATLAB. I'm on an individual compute node. I'm on I31-3, and I can now run commands in MATLAB. I can run this code, and I can run this code however I want. And I can run it as if I was just on my desktop. So this Open On Demand is actually one of our newer resources, and we're still working out the bugs. We're still working out a few bugs, but so far it's been very stable and very good. So if you don't want to mess with the terminal, you can always use Open On Demand. So are all these resources free for FSU faculty? Yes, actually. So if you sign up for an RCC account, signing up for an RCC account is free, and what it will do is it'll get you a home directory with 150 gigabytes of storage, and it will give you access to everything on that HPC partitions list that says general access, and you can use that for free. And the HPC partitions list here actually it'll give you some limits for how long are you allowed to run for. How many jobs can you start as one individual user? How much memory per CPU can you ask for? And it'll also give you some defaults. Anything here that says general access is free for FSU faculty, staff, and students to access. So lastly, thank you all for listening, and are there any final questions? So regarding multi-core, I've tried using Par4 before, but in my applications which involve diffusion, the result of every iteration depends on the previous one, and it's really inefficient. Is there a straightforward way to make this more efficient? So the biggest problem with multi-core is that loop dependence. So one of the ways you could, so there are some ways of messing with that to get it to be a little bit better. One way to do that would be to control exactly how you break up the loop. And just with the basic little Par4 example we gave, it doesn't tell you how to do that. But if you go to the MATLAB documentation, then you'll see that there's actually a whole bunch of other, well, where did that go? You'll actually see that there's a whole bunch of other examples of there's a whole bunch of other things that you can do. You can actually specify clusters. You can specify a whole bunch of options, and the best way to do that would be to try to make sure that you know exactly how your loop is being broken up. So you say, for example, you know that 1 to 5 is on process 1, 5 to 7 is on process 3, and then at the boundaries you'd need to make sure that the code can explicitly access the previous value. So I think I know where you're getting with that, and it's either finite difference or finite. It's probably finite difference, maybe finite element method with that. And yeah, with that, the best thing to do is to make sure. Okay, finite difference. Yeah, the best thing to do is to make sure you know exactly how your job is being broken up, and to make sure that at the boundaries you are explicitly communicating between processes. And a good way to do that in MATLAB would be to store those boundary values as temporary variables within the Par4 loop, and that should speed up the calculation a little bit. So, sure. So one and also I should also mention, if you ever run into problems with this and you need help with parallel MATLAB, particularly if you're working on RCC, you can always email support@rcc.fsu.edu, and we'll be happy to help. So one confusion is that 150 gigabytes have for free versus the partition. Can you clarify these concepts? Okay, so the 150 gigabytes you have for when you sign up for an RCC account, that is storage. That's independent. That is independent of the partitions. That doesn't have anything to do with that. The HPC partitions are basically the way we take our computer cluster. It's basically how we chop up the computer cluster into who gets to use what when. So the only things the partitions have anything to do with are just computing time. So if you need 24 cores, it doesn't matter where your data is being stored. It doesn't matter where your data is being stored or for how long your data is being stored. If you need 24 cores to work on that data, then you need to ask for 24 cores from a specific partition, either general access, backfill 2. If you have an advisor that's got their own partition, it would be from them too. So the partitions are really all about hardware, whereas the 150 gigabyte storage that's just our file system. That's just dumping data onto our system and putting it somewhere. Does that help a little bit? Okay. Perfect. Thank you. Any other questions? If not, I think we are coming up on time here. And thank you all very much for attending, and thank you all very much for listening.